All right, couple of announcements slash reminders, whatever. Tonight, tonight is 5 to 6 p.m. in S109 Raspberry Pi tutorial on using Pi with your laptop without a monitor and keyboard. So if you want to learn how to remote into your Raspberry Pi and have a full graphical Unix operating system like this sitting on your laptop, that's what we'll be doing tonight, showing you how to do that through an Ethernet connection without having to plug it into an external monitor and stuff like that. Then from 6 to 8 in S109, we are watching The Art of Self-Defense. That'll be on the big screen TV in there. So that's a Hulu specific, so unless you have Hulu, you can't watch that at home. Tomorrow, 6 to 8 p.m. in Makerspace, we have First Tech Talk. And this is Eric Johnson from Aurora WDC. It's a AI machine learning company. They would call themselves a business logic company. That should be pretty interesting. He's leading a lot of the things in downtown Milwaukee. I was at a conference last week and down there where they brought in folks that have some background in the AI field, and they're looking at, trying to decide where Milwaukee should invest today's dollars so that they're positioned correctly for what AI will look like in Milwaukee over the next 5 years, something like that. And Aurora WDC is the company that got selected to actually do that research work. And let's see, what's Saturday is the hackathon. What time is the hackathon? 9 to 9. And that's by the Makerspace? Or is that here in CS? I think it's here in CS. See Slack or Josh Appel for details.
Are you requiring this for the classes?
I'm not requiring it, but I strongly encourage you to go to it. A lot of learning takes place in those things. I think all those things were posted last week on Slack, where Josh wanted you to email him. 8 teams of students will compete to make an impressive project using Python and tkinter. So he needs names, belt colors. Anybody who has an orange belt or higher will be provided a basics article to get kind of up to snuff on the tool. So you should probably contact Josh Appel as soon as possible if you're going to that, to make sure you're on the list and he can create groups.
Well, food's gonna be provided.
Huh?
Food provided.
Talk to him, I don't know. Okay. But once again, make sure you're checking Slack often, because the stuff we put up here is not just this stuff. We also put up internship announcements and things like that. And I'm not going to feel sorry for you when you come to my office and say, oh, I'm looking for an internship, but I referenced the 10 different things we put up on Slack. So, oh, I don't have notifications turned on for general. I'll just laugh. All right. So make sure you are checking Slack often. And then for us, we are working with our linked list, what added index, those things. So we have our link. Go ahead.
So I did the homework on the desktop. If I wanted to get from my repository onto my laptop, how would I use like git pull? Is that
It's git clone.
git clone?
Yeah. So if you have a repository file out at the terminal, you would type in git clone and then the full .git file, like the full URL to your repository, and it'll download it. You just Google it. There are 4 million examples. All right, so there's our linked list. Here's our node. Oh, it's flipping back between those. Okay, so for today, that was the previous homework, right? So now we are adding an index, getting index, remove index. Does that look correct? All right, so we have those 3 methods, and we're going to go into linked list CPP. Did I start writing those yet? Nope. So I'll just insert these down here.
They told them already to. I don't know if I like just minimize.
All right, so these are the 3 methods that we are adding and then we are testing. So add at index, again, we should have drawn a lot of pictures, right? We can do this fairly easily for a couple of our test cases. So we can ask the question, if index is equivalent to 0, then we might as well go ahead and call this add front payload and just let him take care of it, right? Else if index is equal to this dot count, then we can say this add end payload. And you could decide to be clever or something. You could say if it's greater than or equal to this dot count, then we'll just put it at the end or something. You could decide how picky you want to be. All right, else we are placing somewhere in the middle. So that's the problem we're solving for this else. All right, it's not at the front, it's not at the end, somewhere in the middle. So we want to go and draw the pictures to figure out how do we do the somewhere in the middle stuff. Okay, so for example, if this is currently my, we'll rename this guy N. Disconnect a couple of these things. All right, so let's say I'm going to put in this node and I want to place it at position 1. So not at the front, not at the end, but somewhere in between. I want it to become the new position 1. So how do I accomplish that? Well, I can move up to the position of where the guy before him should go. Then I can tell, well, let's go ahead and create our N first. So we'll create a node pointer N is equal to a new node passing this guy payload. All right, so there is our empty node N, this guy right here. Now I need to get myself positioned in my list at bucket wherever index is -1. So I know this guy's going to be at bucket index. So I need to start at the beginning of my, maybe call this guy cur node. Start this guy off at this dot head. And then for int I is equal to 0, I is less than index. Okay, so if we have our list of 0, 1 here, so we have at least a 2 list, and I want to get to 0, I need to keep going while it is less than our index, probably minus 1. So I need to show up 1 before him, right? So I need to start at the beginning of my list. I know I want to get to 1. I'm currently at bucket 0. I know that's where I want to stop, is at bucket 0. So the question I should be asking here is I'll start at 0, and I want to stay less than index minus 1. I want to position myself at the node immediately before where I'm going to be inserting this guy. Okay? So every time I get into this loop here, I'll set cur node equal to cur nodes get next node. So I'll set him equal to his own next node. So after this, cur node points to the node right before where n should be inserted. So here we'll call this guy cur node. So that's what it looks like right now. Cur node is the guy right before it. So now what do? I need to make n next node point to the same place that cur node's next node points to. That's step 1. So n set next node to cur node get next node. So this guy's, we're going to set this guy's next node equal to the same thing as this guy, cur node, what his next node points to. So now both of these guys point to this place here. Then I can say cur node set next node to n. Go ahead.
So even though so because they're different, technically different nodes, is what you the two nodes that are, even though they have the same exact payload and next. And
I just drew the picture. I didn't write. Yeah, these are completely separate things.
yeah, but they're pointing, but the second one's now pointing to one that's similar to it. Basically.
Forget about the contents of these nodes. These are each nodes.
Right.
I just didn't redraw the contents of them for our example. Just we have 3 nodes on the screen and we want them to appear in this order.
Right.
Yeah.
Okay.
All right, so now we have our cur node pointing to the new guy pointing to where our cur node used to point to. So he's been inserted into the list. We have added a new guy to the list, which means we need to increment count, right? So we'll say this count plus plus. Go ahead.
So I was under the impression that cur node made a new node that is equal to the head node. So if that were true, how come it alters the original?
Well, it doesn't make a new node. It just points to the beginning node. So head already exists. We don't want to change head because if we change head, then we lose track of the beginning of the list. So we just create another variable here that points to the same place, that they both point to the beginning of the list, and I can change this guy, and we haven't lost track of head.
So it just gives you another pointer towards the same node.
Correct.
Okay, that's actually
All right, so if it's not the front or it's not the end, go ahead and create our brand new node. This is the node we will be putting into our list. Then create a pointer that points to the same place head points to. So this is not creating a new node. This is just creating a second way of pointing to the front of the list. Then zip through our list, getting ourselves positioned, getting kernode positioned at the node right before the node we're inserting. And we know if we're inside this else that we're dealing with at least a current to list. There's at least 2 elements already in our list before we add this thing. So this will position kernode at the node right before where we want to be. Then we'll tell n, our brand new node, to set his next node to point to the same place that kernode currently points to. So kernode points to what used to be bucket number 1 in our example. Node n now also points to what used to be bucket number 1. That then frees us up to reconnect kernode. Kernode set next node to n. So we are preserving the place kernode points to right here, which then allows us to change kernode's next pointer. And then we'll increment count. We have added something to our list. That make sense? All right, so that should be add at index. Get at index is going to run us in our list to the value we want to get and then return that value. Now we could ask the question, if index is 0, then go ahead and just return get front. If index is count minus 1, which would be the last legal bucket if we're treating our linked lists like arrays. So if count is 5, legal buckets are 0 to 4. So if index is count minus 1, we'll just go ahead and get end. We could certainly do that. I'm not sure it gains us that much here, but it's good practice asking those questions. So if index is equal to 0, then we'll return this get front. That does not remove front, it just gets front. Because we also have a remove front, right? Yeah, get front gives us the payload at the beginning of the list without removing it. Remove front actually removes it. All right, so if index is 0, if the position we're looking for is the first element, we'll go ahead and return whatever get front returns. Else if index is equal to count minus 1, then we'll return this get end. All right, and it's equal to count minus 1 because if our count says there's 5 elements in our list, the last legal element would be bucket 4. Now, again, you could choose to be cute with this and say, look, if you give me a giant number, I'll just give you the last thing. So if you give me something that's greater than or equal to count minus 1, I'll just assume you mean the last element. That's fine. I don't know if that's great programming practice, but we're not doing much error checking here, so you can decide what you want for right now. We can just assume we're always calling our code with accurate inputs. All right? So if you're asking for the front, I'll give you the front. If you're asking for the end, I'll give you the end. Else, you're asking me for something in between. All right? Now, we actually could put the logic we're about to put inside the else. We could have put that just globally inside of this get at index, because we're just going to have our for loop, same thing we had before basically. It's going to run kernode from bucket 0 up to the position we want, and then return that payload. So we'll go ahead and say node pointer kernode is equal to this head. So again, this guy gives us a second pointer to the front of the list. It's allowing us to preserve head. We do not want to be changing the value of head unless we are adding something to the front of the list. And even then, we want to be very careful. That idea of that head node pointer is incredibly important to how linked lists work. We have to keep track of where the front of the list is. And today we're going to start talking about keeping track at the end of the list as well. But these are things that we need to make sure we're keeping track of, because it doesn't matter if we have 5,000 nodes in our linked list. If we lose track of the beginning of the list, we've lost the list. And it's because we don't have automatic garbage collection. We just have a floating memory waste thing that we have no way of getting to, other than, I suppose we could write some sort of loop that just walks through memory, like checking each bucket of memory, saying, did I find something that is a node? Do you respond to this kind of message? Kind of like when we put satellites out into space, we have like a record playing on it and speaking English, like the aliens are going to speak English. We just assume, right? But the universal language is math, right? That's what all the movies say. They send us the instructions to build the death ray and stuff. Yeah, so do you know that a fun fact, as Sheldon would say, that Nikola Tesla one time tried to pay for a hotel room with a death ray? True story.
That's an awesome deal, man.
Well, he was working on producing his death ray. He was an experimental physicist with electricity, and he had a lot of funding from some very rich people. And then when he lost his funding late in his life, he couldn't. This guy had so much of our infrastructure today is built on what this guy invented, but he was basically died a pauper. So he tried to pay for a hotel room with and they took it. They said, okay, gave him the blueprints of the death ray. That might have been the time he died in the hotel room. I don't know if it was that hotel room or I think somebody killed him.
They used the death ray.
Yeah, I think they killed him. And I might be misrepresenting this because I watch a lot of documentaries, but I'm pretty sure this is accurate. I think he was believed to be murdered and all his documents, blueprints, and things like that were taken.
What's the name of this guy?
Nikola Tesla. Famous guy.
Yeah.
Go ahead.
If you were just like programming this by yourself, just from like a logistical standpoint, would you have done the get index functions first? Because the logic kind of seems like it would carry over better. Like rather than building the get head and get tail.
Oh, I see what you're saying. Maybe. Because really, get front, get end, get head, get tail doesn't necessarily, they're meaningless if you have a global catch-all get index.
Yeah.
So I maybe just wouldn't even have written them.
Okay.
But because of the way that, I might teach it, where you kind of,
Yeah.
the front and the end of the list are much more, they're safe places compared to the middle of the list. The middle of the list gets a little bit more sketch. And at that point in time, not that it's difficult, but at that point in time, you want to have had practice drawing your pictures. So I guess your question is if I were writing it myself, I would probably just have a get index, not a get front, get end.
Yeah.
I was just slapping a linked list together real quick. Yeah,
This is the Serbian American inventor, right?
that would be him.
Because it says here his death was different. It says in the fall. It says at the age of 81, he left the hotel to make his regular commute to the cathedral to feed the pigeons. While crossing the street a couple of blocks from the hotel, Tesla was unable to dodge a moving taxi cab.
I don't know. That sounds pretty.
And 3 of his ribs were broken in this accident.
So he was walking from his hotel to go feed the pigeons and got hit by a car.
Basically, yeah.
That's not suspicious sounding.
But he didn't die. He didn't die from the initial impact. It was later in his room. He died of a blood clot.
Mm.
And then I read that.
Of course he did.
Yeah. Well, and he left the do not disturb sign, and then 2 days later
We found him.
Yeah, and they found in a box plans for death ray stuff.
Yeah.
I think, so.
See, this is all conspiracy. This is hidden in that same box with the JFK assassination.
Yeah,
Same place.
The taxi cab was not a coincidence.
Maybe it was, but it makes the story sound pretty interesting.
Yeah.
It does. Taxi drivers, watch out.
Okay.
The longest would be I've ever seen.
Yeah, he was the inventor of alternating current, Tesla. So the type of power we use today, like when you plug your laptop into the wall,
The outlet, yeah.
that's Tesla. The other guy was making direct current, and he was electrocuting elephants to prove how powerful it was.
Dang, if only he lived just a bit more longer. I wonder if his death really ever came to fruition.
He was like 86
He's
at
also,
the time.
what we named the Tesla coil after.
And the Tesla car.
Just,
No, that's the company's.
Oh, okay, I see.
That's where the name comes from. For the electric car, get it? Haha, Tesla.
yeah.
All right, so get an index. We're going to go ahead and if it's 0, return 0. If it's the end, return the end. Otherwise, we'll go ahead and get ourselves to the beginning of this list, and then we'll go ahead and run to our index. In this case, we want to get to the actual index, not the guy right before the index. So we'll say for int I is equal to 0. I is less than index I plus plus. And we'll say cur node is equal to cur node get next node. So that will run cur node down the list so that it's pointing at the index that we want to return. Okay? And we'll go ahead and return cur node get payload. That's the value that lives at that index. That make sense? All right, so it's important that we understand what code like this is doing because it's going to be a rinse, lather, repeat thing. We're going to be using stuff like that over and over and over again as we traverse linear linked data structures. Give yourself a second pointer to the beginning. Run down the list, making yourself equal your own next node over and over and over again until you're positioned in the list where you want to be. Then in this case, we're not removing anything. We're just going to return the payload we're currently looking at. That's the get index. Now, remove index is going to be similar. We can ask our same questions. If index is equal to 0, then we can go ahead and return this remove front. We already wrote that code, and that will also decrement count for us, right? So don't double decrement count. We're relying on remove front to remove an element from our list. Count will go down because remove front will make that go down. Else if index is equal to count minus 1, return this dot remove end. Else we're removing somewhere in the middle. All right, if we're removing somewhere in the middle, I need to position myself at the guy immediately before the guy I'm returning. So we're back to our picture here. My list currently looks like this. I've said I want to remove, for example, bucket 1. So I need to get myself to the node immediately before the guy I'm removing. All right, so I'm going to run him to that position. So for int I is equal to 0, I is less than index minus 1, I plus plus. And we'll go ahead and say cur node is equal to cur node get next node. All right, so now cur node is pointing at the guy right before the node we want to return or remove. So cur node currently looks like this. It's pointing to the node right before it. Here's the guy we ultimately want to get rid of. Okay, so I need to, now if I just set cur node's next node, if I try to do this, I can't even do that right now, I will have lost track of this guy. So I'm going to need another pointer pointing at the guy we want to remove. So here we have a pointer here called guide to remove. So we're going to set guide to remove equal to cur_node.getNextNode. That's who guide to remove will be. Node pointer guide to remove is equal to cur_node getNextNode. So guide to remove is equal to whatever cur_node's next node is. This guy here. So both of these guys point to the same dude here. Yeah.
Guide to remove was initialized at the beginning, right? At some point in your methods.
It was initialized right here, the last line I wrote.
Oh, okay. So you just had that kind of variable.
We used it in one of our other methods, so I just
Oh, okay.
decided to use the same name so I didn't have to retype in there.
I see. So you can do that with the methods, but like without worrying about it changing or anything.
Well, I could have called this guy Elephant if I wanted to.
Yeah, like what I mean is that like for similarly named nodes. Sorry.
You typically want variables to have meaning to them.
Right.
So if this is going to be the guy I'm going to be removing, having a variable named guy to remove kind of makes some sense, right? So in previous methods like remove front and remove end, I had a guy I wanted to remove, just like in this one. I have a guy I want to remove.
Okay.
So that's just choosing to use the same variable name. All right, so now cur_node points to this guy. Guy to remove also points to this guy. This frees me up to set cur_node next node equal to guide to remove's next node. Cur_node set next node equal to guide to remove get next node. That's this move right here. Cur_node set next node. This is his next node. We're setting it to something else. What are we setting it equal to? Guide to remove get next node. This guy here. So now cur_node and guide to remove both point to the same next node. Finally, I like to fully disconnect. So I want to do that piece right there. So I want to set guide to remove's next node. This sets his next node to null. So a 0 represented as a node pointer is the null value. Not to be confused with me giving that next node an integer value of 0. In this case, 0, in our language of decimal numbers, digits, 0 means something. In this case, 0 means something different. 0 means nothingness, null, because we're using it as the representation of the pointer this guy is pointing to. So we're going to say 0 is an illegal address. So if a pointer points to an illegal address, that means it's not pointing anywhere. All right, so now this guy is fully disconnected from our list. We can say, okay, we've disconnected the guy we want to return, guy we want to remove. We've reconnected the rest of our list. Everything looks legit enough. Ultimately, I'm going to give myself guy to remove get payload. So I'll remember the payload that I'm going to return because I'm ultimately going to be returning val to return here at the bottom. But before I do that, I need to clean up my mess. So I will delete guide to remove. Go ahead.
Why is that you need to delete before doing return? That was one of the issues that I had with like setting val to return, delete return. I had those like in a different order, and that gave me a segmentation error.
Yep.
And I wasn't sure why.
So let's play it out. You had it like that. It gave you bad news, right? You deleted first, then got the value. All right. What does this do? Go ahead.
Just wipes it out.
It literally gets rid of that memory. Then what are you doing on this line right here?
Oh, no, I did have the definition before the delete. I think it was maybe I put the delete last after the return.
Oh, because return makes a method immediately end.
Oh, okay, that makes sense.
Yeah, method would immediately end, and then we would have never deleted it. But yeah, so if we've already deleted guide to remove, we can't start asking nothingness any questions. So we need to make sure that any important information we get from the hostage, we extract before deletion. That sounds like a made-for-TV movie, doesn't it? Yeah. We extract the information before deletion. Go ahead.
It's technically still in memory though, right? It's just the operating system is now freed it up so another program can use it.
Correct. Yeah. So the point there is it has not actually erased the node from memory. It's just unmarked that memory location as now being an available memory location for the operating system to hand to somebody else who needs memory for something. Yeah, it's no longer reserved for you.
Could you remark it? Like, let's say you wanted to delete it and then remark it again, like if you wanted it back, or does it have to
You
be-
probably shouldn't have deleted it then.
Well, yeah, that's
You could ask the operating system to allocate some memory for you, and maybe you'll, through luck of the draw, get that value back. Or you could remember this memory address and then just take it back, hoping that nobody else was assigned it.
right.
Because at that point, you're living off the grid, right? Because a good programmer would always use memory that they have permission to use. Who gives you permission to use the memory? The operating system. Well, if we tell the operating system we are done using this memory, and then we go about using it again, we're breaking some rules.
Right. Okay.
All right, so we'll go ahead and extract our information, then delete the memory, finally return the information we extracted. Remembering that the return statement makes a method immediately end. So if I put return before this delete, the delete will never occur. Go ahead.
You forgot about minus on count.
Thank you. So sometime before my return here, I need to say count minus minus, because I have indeed removed something from the list. My list has one fewer things in it than it used to. All right, that makes some sense. So that should be remove an index, and we have get index, and we have added index. So we should be able to test this. Let's go into driver. All right, so we added a 1. So now we have a 213. Let's say LL add at index, and we're going to tell it the index we're going to put this guy at. We're going to put it at index 1, and let's put a 7 there. So now it should be a 2713. Let's just start with that. All right, so 1 to the front, 2 in front of that, so now it's 2, 1, 3 at the end, 2, 1, 3. Then we're going to make a node 7 be the new bucket 1, so it'll be a 2, 7, 1, 3. All right, I'll announce it again because we had a couple of students who had a similar type problem. Remember that if you have any GCH files out here, that means you have a compiled header file. You'll get errors in your code because if you've changed that header file, so for instance, if I've come in here and I make a change to my linked list header file here, and I have a previously compiled version of this header file, which gives you a .gch file, it won't know about your changes, because you have a compiled executable ready, ready for linking version of this, and it'll scream at you. So I would say before you try to compile, make sure you have no GCH files in here. If you do, delete them. That way all your header files will get renewed with their current up-to-date code. So if you do that, and then you always do a G++ of all the C++ files, then it'll take care of itself. All right, so I should have my a.out, so ./a.out, there's my 2713. So that is adding at index 1. All right, so now let's test my remove. So we'll go ahead and say int val is equal to, actually let's do get index 1. That'll give us our, actually let's do get index 2. That'll give us our 1, the value that comes after the 7. And then I'll go ahead and do a standard So I'll print out val. So this should give me a 2713, and then this should give me a 1 for my last one here, because I'm getting bucket. And I'll go ahead and display again. I'll just display at the end. I'm going to get that 1, and then I'm going to display proving I didn't actually remove it. So there's the 1 that I got. Then I displayed my list 2713. I didn't actually remove it. As opposed to me saying remove index. Is it remove index or remove add index? Remove index. And I'm going to say remove index 2. So this will still print out that 1 for me, but then when I display it, the 1 will have been removed from my list. So there's the 1, but now we see my list is 273. The guy has been permanently removed from my list. All right, questions about any of that? All right. So let's do this. Cin will let me read it a value. I'm going to get a random number quickly. All right, let's see how this, I'm just going to steal those 2 lines of code. We'll experiment with it real quick. I want to see how this random number generator works. All right, so this first line here, this is, I probably have to include time.h. Where does time come from? C time. Okay, so we are seeding the random number generator. That's what SRAN does. So this kind of gets the ball rolling, and it prevents, there's a whole area of computer science dealing with sources of true randomness. They're actually difficult to find. So they're using the current clock to give us our initial value for our random number generator. So this is just saying give us current time. Probably it's giving it to us in milliseconds, is my guess there. So we are getting the current time in milliseconds, and if we want, we can just print that out and see what that looks like. We'll run that real quick. I'm guessing that's going to look like a big, crazy millisecond number. Yeah. So usually that would be number of milliseconds since 1970. So this is called Epoch Time. So that's our the value we're using to seed our random number generator, whatever. I'm guessing that if you don't seed it, it probably grabs some sort of default seeding thing, but what you might get is you might get the same random number over and over again. We'll experiment with that here in a second, just as we've effectively run over to Home Depot. We've bought some tool that was on sale, and I'm sure I've used this one at some point historically, but we came home with the on sale tool that we bought. We're going to experiment with it a little bit, make sure we understand how this guy's working so we can use it in our program, right? Okay. So I'm going to go ahead and here, I'm actually just going to get rid of our linked list stuff here for a little bit. Actually, here, let me do this. Did I tell that last class? So you don't really want to watch the video. You just want me to tell you again. It's just a text file. You create a normal plain Jane text file that just happens to have your commands in it. These are the commands. I'm removing my a dot out. Then I'm saying git add everything. Then I'm saying git commit -m, and I'm just always giving it the same message for committing. And then here's my git push -u origin master. So these are the commands that you would have issued by hand one at a time. Put them into a file, and then out here, just change the mode of that file, change it to 755. If you want to learn how change mode works, just Google it, but you'll GitHub push change mode 755, and now that guy will show up as green. And then to run it, just do a /, and it will be as if you typed in those commands.
What do you save the text file as?
Just regular file.
Yeah, I could have called it .lol if I wanted to. Yeah, Unix doesn't care because its executableness has nothing to do with its extension. It's not looking at a .exe. It's looking at its mode, which is 755, which is read, write, execute by the owner, read and execute by the group, read and execute by everybody else. All right, so now you have my current version of the code up on GitHub if you wanted to look at that in the middle, because I'm going to start removing a couple of things. All right, so I'm just going to get rid of our linked list thing here for a second. I'll go ahead and print out our random variable. So this is an integer that we're getting from the rand function that we have previously seeded with time. So historically what might happen here is if I run this program, let me get rid of the rest of my linked list stuff. If I run this program 5 times, I'll get probably 5, well, I'm guessing it's going to give me int in the range of all integers. So I'll get 5 different numbers. Now, if I didn't seed it, I would get the same number 5 times. So seeding it guaranteed that I got new numbers. And I'll explain it as we kind of go through here. So there's that number. I expect the next one to be a different number. Interesting. I ran it too quickly. So the millisecond didn't change. Now, so that indicates it's probably going to do what I said. So if I don't seed it, I think I'll always get the same number because it's always starting with the same sequence of random numbers. So not true randomness. Make sense? Now, if I asked for 10 numbers in a row, I would get 10 different numbers, but I would always get the same 10 different numbers. So if I came in here and I said, let's just put this in a loop, we're going to I is equal to 0, I is less than 10, I plus plus. Not great programming practice to redefine that every single time, but just deal. So there's those values. Run it again, you get the same 10 values. But if I seed it initially and I'm picking a source of, we're going to call this pseudo randomness. Now when I run this, as long as I'm not running it too quickly where it's the same millisecond, I should get different values. Make sense? Well, we'll call it random enough. All right? So let's say that, and we'll cut these values down a little bit just so they are a little bit more palatable for us. So I'm going to create a linked list pointer LL is equal to a new linked list, and then I'll go ahead and say LL dot add end a random integer, and then we'll say LL dot display. So now I should have a linked list with 10 elements in it, right? So there's my linked list, so on and so forth. If I want to make my list a lot bigger, I can add more things. So I'm going to just set it at around 20. I think that'll be a good number of things. All right, so now I have a linked list that's containing all these values. Now what's nice about this, again, we're seeing the arbitrary strength of linear linked data structures. That is to say, I didn't have to define an array and say, oh, you're capable of holding 10 elements or you're capable of holding 20 elements. I just created a linked list and I started loading it with stuff. He stretches or shrinks as needed. Make sense? All right, so that's the beauty of a linked list, but not to be confused with those values not necessarily having, well, here, let's just prove an under the hood thing here. So I'll go into linked list CPP. Actually, I'm going to create a second display method. Call this guy display pointers. So instead of displaying the values that live there, I'm going to display the memory addresses of where these nodes live. And what we'll see is that with arrays, it's contiguous memory. All those memory addresses are right next to each other. With this, we're very likely not going to see these guys sitting next to each other. They're going to be all over memory, or at least not right next to each other. Where's my display? Oh, farther down, I guess. I'll just put it next to where our current display is. There we go. All right, so I'm going to just steal our code we had in here before, where I'm going to take kernode on a voyage through my linked list, but instead of printing out the payload, I'm going to print out kernode. Kernode is a node pointer. What does it mean for something to be a node pointer? Yeah. Yep, it's holding a memory address. So I am printing out the value of kernode. Excuse me. The value of kernode, which is a memory address, because kernode is a node pointer. So now in here, what did I call it? Display pointer or pointers? Pointers. All right, so I have a second version of display. The first version shows me the values I've stored. The second version shows me where those values are in memory. And these guys should not be linear in memory. Okay, now we actually are seeing several that are close to each other. Because we're doing it so quickly and nothing else is happening in between. So these are bytes, so they're giving us 20 bytes of space. Well, the problem is our program isn't doing anything in between.
Right. Yeah.
We're just sort of zipping through and adding a bunch of numbers to it,
Right.
asking the operating system for the next available spot in memory.
So it's going by basically, so by the time it gets to its next number, it's just going up by like a certain increment for the beat, or like for like the second one it's D-O, and then for the next one it's D-O.
Yeah, well, this is hexadecimal counting.
Well, yeah, but it just like implies sort of like pattern.
Yeah, so this is 90, and then this is 11,
Right.
0. 9, 0, 11, 0. 13, 0.
Yeah.
15, 0. And then we bumped up a level here, so now we have this E became an F.
Yeah.
And now we're at 10, 30, 50, 70. So what's interesting here is that these do happen to be stored in contiguous memory, but it was not required. And we are assuming that. But it is kind of an interesting thing, since we know these are stored in contiguous memory. We could actually reference them like a array. Let's see if it protects us from this. This could be kind of fun. So I'm going to go ahead and say standard cout, and we're going to say LL at bucket 3. Which will be that'll give me the memory address. Actually, that's the node, LL at bucket 3. Well, no, it'll be a memory address for right now. It doesn't like me, so I can do this then. And this is bucket 3, so the fourth element. 0, 1, 2, 3. So this is EF0, EA0. Actually getting output from him.
Did you end up changing under linked list.ccp for the display pointers?
Or the display pointers.
Yeah, so like for
Oh, this guy?
Yeah.
I just gave myself another function, and instead of
Yeah.
printing out the payload, I just printed out the actual cur node. I just wanted his memory address. Show me where you put all my nodes throughout memory.
so just get rid
And
of
it just happens to be that it did store them linearly here in memory. DDCEA0. Yeah, I'm in the right memory space, but I'm not walking through node size steps because it's just walking through memory address sizes where this is giving me 20 bytes per. So punchline is you could pull it off doing this. You would just have to use kind of a funky offset, knowing what the size of the memory hop is. So in this case, it's plus, like we saw, it's 3 times 20. Oh no, I'm going way too far then. So what does it think? It's adding to this 3 times the size of whatever a node pointer is. But a node pointer is something else. Am I able to do that? It's kind of academic anyways. It just happens to be because we are getting values that are next to each other in memory, even though they don't have to be next to each other in memory. But whenever we're working with linked lists, we could just make the assumption that there is no guarantee these guys are in contiguous memory. So if we want to traverse the list like we're doing now, we have to start at the beginning and walk until we bump into other things. All right, so let's just leave it at that. I'll leave my display pointers in there because it's interesting, and at any point in time, if we start adding things a little bit less often into our linked list, we'll start seeing that the memory isn't right next to each other. Go ahead.
Is part of the reason that the memory was right next to it in your machine because you have so much memory that it's like less?
No, but when you run a C program or C++ program, it's given user space, a chunk of user space for memory. It says your program will run in this space, and I'm not asking for anything in between. You know, my entire program right now, all it does is add stuff to my linked list. If I said int a equals 7 one time in there, I would at least throw it off by the size of an int.
Okay.
You know, so it's just, you know, if you're the memory manager, you're the one handing out available memory addresses, you know, and you have this stack of available memory when the program first starts, and the only thing you're ever being asked for is a place to store a node, you're probably going to hand those out in order, right? I mean, that's my next available bucket for a node because I haven't done anything else in there. So this happens to be luck that they're next to each other, whereas with an array, they're guaranteed to be next to each other. Arrays have to work that way. So I was kind of operating off the idea here that you could sort of kind of treat this linked list like it was an array in this particular circumstance because it happens to be in contiguous memory. I can choose to walk through memory like it's an array, not that that's any benefit to me, but I could choose to do that. Yeah, we would actually see if I went through and I removed some values, I would we would see it no longer be in contiguous memory, because I would have gotten rid of an old variable, old value, and then it would have added a new one later on, giving me new memory. All right, so I'm going to put this back to display. Okay, now, would we agree when I run this right now? We're back to showing the values that are in the list. Those are pretty big values. Let's shrink them down just a skosh. So I'll mod these by 1,000. So this will give me values between 0 and 999 in my linked list. So there's my linked list. Not in order, right? What if I want those to be sorted? How many of you are thinking merge sort? Merge, is this merge? We won't do merge sort yet. Although merge sort would be pretty compatible with linked list. All right, so if I want to sort these guys, I might have a void sort. And this guy ultimately rearranges the linked list such that it is in ascending numerical order. All right, so first thing in your head is don't immediately jump onto Google and say, is there a linked list sort function? Because guess what? Your linked list, you invented. That's not something built into the C language. There's a standard template library that does give you linked lists and stuff, and it probably does give you a sort function, I'm guessing. You're not allowed to use it. You have to use your linked list. It might be able to call, I mean, you don't have to call it linked list. You can call it whatever you want, but you have to make your monstrosity sort itself. So if I were to display it, so for example, here inside driver, if I were to say LL display and then LL sort and then LL display again, it should now be sorted. So I'll go ahead and give myself a waste of time header here just to let it compile. So sort is a legal function right now that does nothing. But it is now something you can call as part of your linked list, which means when I run this, I will display, just like I did before. Then I'll call sort, which magically accomplishes 0 lines of code. And then I'll display again, seeing that it's not displayed any differently than it was displayed a second ago. You might want to put a little line in there just as a separator. Put some asterisks in here. There we go. There's our divider. 822s at the end of the first one, 822s at the end of the second one, and it says they're not sorted. All right, so you need to make your sort work. I'd encourage you to go back to what we had previously looked at, and then you can make your sort work however you want. You can invent your own sort if you want. But what I'd encourage you to do is look at our code from last year called insertion sort. I actually teach a modified insertion sort, where so my insertion sort kind of works like a bubble sort, where you have values. So let's say you have 3, 1, 7, 4, for example. And what you do is you start at the second list to the top. Remember that thing where we had the follower? I had the little skull and crossbones, the follower follows. So should a 1 come before a 3? Yes, it should. So we'll swap those two, and the follower follows. Should a 1 come before an illegal position? Nope, we're at the top of the list. So now we'll start at the 7. Should a 7 come before a 3?
No.
Nope, so we're done. Should a 4 come before a 7? Yes. Swap those two. The follower follows. Should a 4 come before a 3? Nope. So we're done. Now we're off the end of the list. We're out of things to check. Our list is now sorted. So remember, insertion sort starts at bucket 1 and goes all the way to the end and maintains our next starting position and then checks the current starting position against the guys above him until he can't bubble to the top anymore. Make sense? That's the one I would encourage you to write here. Keeping in mind that in order for you to write a linked list version of this, if you decide that I need to swap my 3 and my 4, for example, what does that actually mean? It means that this guy needs to become the new bucket 1. My bucket 2 needs to be removed. He needs to become the new bucket 1. So I'm doing a swap, but I can't just do it like I did with arrays. Remember arrays, I said, okay, I'm going to have a temporary variable, so I'll store bucket 1 here, then I'll overwrite bucket 1 with bucket 2, then I'll overwrite bucket 2 with the guy I temporarily stored. I had my copy thing. It's not going to work anymore. I actually am performing surgery on my linked list every single time I need to do a swap. If I need these two guys to be in different orders, I can decide to just do like a heart bypass type thing if I want, or I can maybe remove one of the guys, let my list become its new thing, and then insert him at the position before him, rather. Does that make sense? So you're going to have to practice using your different linked list abilities in order to accomplish this. Good.
Do we already have all the methods we need for this?
Probably. It really depends on how you go about doing this. I mean, I think you can accomplish it all from just remove at index and add at index. That doesn't mean that's the way you'll go about it. Questions, comments, concerns? Go ahead.
If like our linked list on GitHub wasn't forced from your linked list, is there a way we can still pull your files to our linked list?
Yeah, you can do what's called a merge, but the path of least resistance might be just to fork a new repository and start that as your baseline if you want to use mine as a starting point. But here I'll push. Here's my latest, greatest version. All right, remember, today, student, faculty, staff, Bible study, God in, grub, go to the cafeteria, sign in, take your tray down to the terrace room. That's from noon to 1. I'm heading down now and eating in the cafeteria beforehand. And I'll see everybody on Thursday, if not before. Hopefully I see some of you tonight. I see some of you, well, most of you at the Tech Talk tomorrow, so on and so forth.